G'day guys, in this video I'll be talking about radius of curvature, and specifically I'll be deriving the formula used to calculate it. So let's first begin by talking about what radius of curvature even is. And let me start by imagining that we have some particle which is swooping out some complicated path over time. And let's say that the path that swoops out is given by the equation y is equal to f of x, like this. Now radius of curvature is all about asking this question. Can we view this particle at any particular instant, let's say it's here, as if, for that instant, it's swooping out a circular path of radius rho? Okay? As it turns out, it can be viewed that way, and rho is called our radius of curvature. Now you might be thinking to yourself, hold on, at each individual instant, maybe the radius of curvature could be very different. So for example, when the particle is here, maybe at this instant it can be modeled as if it's going around part of this circular path from this circle, right? And the radius of curvature at this instant would be rho, which might be bigger than it was before, okay? Now that's entirely possible, right? So how do we calculate the radius of curvature for each individual instant? Now the trick comes from realizing that because we're modeling this thing as if it's going around a circle at each individual instant, that means we can use circular motion formulas. It shares the same path, velocity, and acceleration, so that means we can use circular motion formulas to find that. Namely, we're going to use this one. ds is going to be equal to rho d theta. And you might recognize this formula as being the formula used to calculate arc length. Okay? So the game plan here is to find ds, and is to find d theta, and then plug this in algebraically to solve for rho. Okay, so let me begin by starting off with the easier one. Let's find ds, the small chunk of arc length just here. Well, we know we can find that by using Pythagoras. We know it's just a small chunk of distance, which is given by the square root of dx squared plus dy squared, right? And of course, we can factor out a dx from the square root sign and write this as the square root of 1 plus dy dx squared times by dx, okay? That was the easier one to do. Let's see if we can work out d theta. Now to do this, what we're going to need to do is we're going to need to zoom in on this picture, right, to help us out. So let me draw this down here. Let me draw our circle, our pretty crudely drawn circle just here, and let me draw the path that this thing is modeled to be at this instant, right? And also on this path, I'm going to draw the gradient of our curve at this instant as well. And this gradient, of course, has a value of dy dx, okay? Now I'm also going to draw a few more things. I'm going to draw the radius of curvature at this instant, like this. And I'm also going to draw the angle theta. Now our goal here is to find theta in terms of dy dx so that we can solve for d theta. So we realize we can do this if we complete this right angle triangle like this, and we can realize that this angle here is 90 minus theta, which means that we realize, because this is a right angle triangle, that this angle here is going to be theta, which means that we realize that this angle here is going to be equal to theta as well, right? And this actually says quite a bit, right? Because the slope here is dy dx. That means the rise over run is going to be dy over dx as well. So that means tan theta, which is opposite over adjacent, is equal to dy dx. So let me write that down to make it a little bit more clear. I'm saying that tan theta is going to be equal to dy dx, our slope. Okay? Now we need to find d theta, so I'm going to differentiate with respect to x for this equation. I'm going to differentiate. So I'm just going to write d dx of tan theta is going to be equal to d dx of dy dx. Now the right-hand side is pretty boring. That turns into your double derivative. But it's the left-hand side, which is going to be a little bit harder to work out. Okay, well, if we were to differentiate tan theta with respect to theta, we would just get 1 plus tan theta squared, right? But of course, we're not differentiating with respect to theta, we're differentiating with respect to x. So we need to times it by d theta dx, like this. Now on the right-hand side, we just get our double derivative, which is going to be d squared y dx squared, like this, okay? So far we've got an expression involving d theta, and we've got an expression for ds. Let's see if we can tie everything together to solve for rho. Okay, but before I do that, actually, I jumped the gun a little bit. What I'm going to do is I'm going to realize tan theta squared can be written as dy dx squared. So let me write this in as d theta is going to be equal to d squared y dx squared times by dx, if you bring this guy over here, all divided by 1 plus dy dx squared. Okay, that's what happens if you solve for d theta from here. Okay, so I'm going to plug this, and I'm going to plug this into here. Okay, let's do this step by step. Rho now is going to be equal to ds divided by d theta, so it's going to be equal to this, which can be written as 1 plus dy dx squared all to the power of a half times by dx. You might be seeing why I'm writing this as the power of a half shortly. And then we're going to times that by the reciprocal of this, right? Rather than dividing by d theta, I'm just going to times it by the reciprocal. So we're going to times it by 1 plus dy dx squared to the power of 1, all divided by d squared y dx squared times by dx. Okay? Now we can do quite a bit of simplifying here. We notice that the dx's cancel off. That's the benefit of using Leibniz notation. Might make a mathematician cry a little bit, but we can do that, right? And we can also group these terms just here, right? Because they're the exact same, just with different powers. And we can write our final answer as our radius of curvature is equal to 1 plus dy dx squared all to the power of 3 on 2, because 1 plus a half is 3 on 2, divided by d squared y dx squared. And we are done. We have found our radius of curvature at each individual instant, and it's given by this formula, like this, okay? Now, before I end this video, I could end it here, but before I end this video, I want to briefly explain why you might see in certain textbooks that the radius of curvature is written with an absolute value sign here. And that's because the radius of curvature can be negative if the circle is on the bottom of this curve, because that would indicate that it has a negative concavity, right? But it's kind of counterintuitive to think of a negative radius of curvature, right? So mathematicians, or mainly engineers, I guess, decided to make it positive just so it's in line with our intuition. So that's why this absolute value sign is here. It's to make sure that our radius of curvature is always going to be positive. Okay, I hope that made sense, guys. Cheers.